All right, let's go ahead and get started. Any questions before we get back into it? All right, so just a heads up about sections 4.1 and 4.2, which we've done previously. The web works for both of those are due on Sunday night. I anticipate we're going to finish 4.3 today. So I'll probably make that one due Tuesday. But just wanted to give a heads up since I haven't collected a web work in a while. Yeah, 4.1 and 4.2 and 4.3 are all going to be coming up sort of close to each other. Solomon?
Do we have our mastery exam on Wednesday?
Yeah. So mastery exam Wednesday. I put something on Canvas in the exam prep area that basically it gives you 50 minutes and it just throws a bunch of multiple choice derivatives at you.
Is it
If you,
huh? Is the mastery exam multiple choice?
Yeah. So that thing I put on Canvas, if you haven't already gone to look at it, I would make sure you go practice, because I think that thing is really valuable. And that's all the mastery exam is, 20 functions, or we do implicit differentiation. So not all functions, but 20, basically find me 20 derivatives. And they're all multiple choice. But yeah, if you haven't already gone to look at that thing on Canvas, go do it, make time for it. What else do I want to tell you? If that's it for now. Yeah, if there are no questions, we'll go ahead and jump back in. So it's been a week, so let's kind of refresh this idea about this second derivative. So like I've asked several times, what does the first derivative of a graph tell you? Of course, what does the first derivative tell you about the function? An instantaneous rate of change, or if I'm looking at a graph, yeah, increasing, decreasing. So if your function's increasing, what's true about the first derivative? It's positive. What's true about the graph if your function's increasing? Has an upward slope as you look from left to right, right? So we said that both of these functions have a positive first derivative everywhere, because they're both increasing. The difference is the second derivative is positive on the left and negative on the right. Why is the second derivative positive for the first graph?
Because it's increasing at an increasing rate.
What's increasing at an increasing rate?
The rate of change. The rate of change of the rate of change is increasing.
I want to make sure the rate of change of what function are you referring to?
The rate of change of f prime.
Okay, so the rate of change of f prime is positive. And the reason I'm hitting back at the pronouns is now we have three functions that we're talking about now, right? So I don't want to leave any of those ambiguous. But a couple ways to say it, like we said last week. F double prime is positive. Actually, you said f prime was positive, it might not be. In general, but I think for this one it always is, right? But in general, saying f double prime is positive, does that mean that f prime is positive? What is it? So all that means is that f prime is growing. It could have began at like -100. So it's increasing doesn't necessarily mean it's positive, and we'll see some examples when we look at some different functions. So in general, I'll just point this out. I mean, you've told me several times that the first derivative of a function tells you something about the rate of change of that function. What's the first derivative of f prime? F double prime. So that same relationship holds. The derivative of a function always tells you something about the function it came from, even if that function isn't itself the derivative of some other thing. So let's look at another graph talking about, or not yet. So this idea we're talking about is this idea of concavity. So if you have a graph whose second derivative is positive, or the slopes are always increasing, then that graph is concave up. Or that function is concave up on that interval. And similarly, if the slopes are decreasing, and by the way, I'm saying that the slopes are decreasing, that is the same as me saying that f double prime is negative. So I'll just point this out here. This is equivalent to me saying this. F prime of x is doing what? If f double prime is negative, what can I say about f single prime?
It's decreasing.
It's shrinking, right? It's decreasing. I can't say anything about its sign, whether it's negative or positive, but I can say that as x grows, f prime of x is shrinking. If there exists a point where I go from concave up or concave down, or vice versa, that is this new thing called an inflection point or point of inflection. So throwing some new vocabulary at you. Any questions about any of these definitions so far?
So that point where it goes from concave up and down is called an inflection point.
Yeah, or vice versa.
Okay.
What do we call it if it goes from concave up to some point where the second derivative is 0 back to concave up? No, not necessarily. So, I mean,
It's called a saddle, isn't it?
no, it's not, and that's why I wanted to bring it up. And this is, it's not easy to think about what the first derivative of a function looks like, but it's much harder to think about what the second derivative does. So, why don't I try to draw you an example of what I'm talking about? This function right here. Actually, I don't even think I did what I wanted to do. But that's okay, we're going to use it. Is there an inflection point on that? No. If you're saying there's no inflection point, then you're saying it's either concave down or concave up everywhere. And those are hard to see, right? Critical points, what do critical points look like on a graph? Yeah, I mean, horizontal tangent line, right? It's way harder to see those on a graph like this. Does this have any critical points? No. No. I mean, there are no, that thing is strictly increasing, right? Mm-hmm. But what I intended to do and what I believe I did is I believe that I put an inflection point there. What's the concavity on the left at that point?
No, down, concave down.
Why is it concave down?
Because it's decreasing.
What's decreasing?
The rate of change.
What's rate of change? F double prime is decreasing.
Yeah.
I don't know if I agree.
F single prime is decreasing, F double prime is.
Okay, that's better. So let's write all those things down. Over here, F double prime is what? It's negative. It's hard for me to say it's decreasing, but I can definitely say that F double prime is negative because F prime is doing what? Decreasing. I don't want to draw the tangents because this is already getting cluttered, but if I were to go from left to right and think about what the tangents look like, it'd be something like this, right? They're steep, getting shallower, right? After this point, so to the right of that point, what's going on? Concave up, and what tells you that? F prime is increasing, right? Or equivalently, F double prime is positive. And since I tried to draw you a function that is, I can take as many derivatives as I want, they'll always exist. And the second derivative is continuous. If the second derivative is negative over here and positive over here, then there's got to be somewhere in here where it's 0. So I think there is an inflection point here. But it's really hard to see those things, especially because you've never had to think about it until now. But basically, you can see that in the first derivative, what are the slopes doing? Like kind of in the vicinity around that point. They're kind of steadying out, right? It kind of looks linear. Solving your question?
How do you tell when the inflection point is?
I'm guessing. So I mean, I have an idea. Like critical points are easy, right?
Yeah.
There's a peak or a valley. or a saddle point. These, I'm kind of guessing as to, I mean, if I go far enough away from it, it's clear that I'm concave down. If I go far enough away from over here, it's clear that I'm concave up. I know there's an inflection point somewhere in here. Yeah. If I put it here, it'd be hard for you to tell me I was wrong. So, I mean, I'm sort of eyeballing. Unless you actually have like a way, like an algebraically defined function, it's hard to be exact about it.
So there's, oh, well, like what the function is there?
Oh, absolutely, absolutely. So what is an inflection point? Like, how did I define it?
When f
F prime is 0, right? You can find, I mean, that's, if you can get your hands on the function, like how it's defined, then we can do those things. But yeah, this, from a graph, the best you can do is sort of approximate. All right, so let's practice a little bit. All of these little subintervals are either concave up or down. So let's just go from left to right. The interval from A to B is what?
Down.
Okay, your vote's for down?
Yeah.
We sure about that? Okay. So yeah, first interval I would say is concave down. How about BC? Yeah, so I'm at this stage, I'm telling you that every subinterval is either up or down. We're not mixing that. Okay. So yeah, everything between B and C is concave up, but since there's confusion, let's talk about it. Can I say F prime is always positive or negative on this interval? Has to change, right? So again, is there a critical point on here? How do you know?
Because if it goes from negative to positive.
If what goes from negative to positive? F prime. How do you know F prime goes from negative to positive? What's like the easy visual marker? Right, so this is valid, right? So critical points again are much easier to see. What's not as easy to see is why the concavity is the same sign everywhere here. What's happening to the slopes as I go from left to right? They're always increasing, right? And that's and the thing I want to point out here is F prime is always increasing, right? But by no means is F prime always positive. So that those two things are not, they don't go with each other necessarily. Just like over here, F prime is clearly positive over here, right? Is F prime positive everywhere on that subinterval? No. So after this point, F prime is negative. But what can I say about what can I say that's always true about F prime in this interval?
It's increasing.
I don't think it's increasing. Otherwise, that would be false.
You're right. It's decreasing.
It's decreasing. So, as we go from left to right, what are the tangents doing?
Yeah, you're right. Okay.
So, yeah, they are getting smaller. We okay with that so far? Okay, actually, I don't think anyone's okay with it. As okay as I can expect you to be for what little we've done. How about CD?
Funny enough, it's CD.
It is concave down, right? So let's say this. What does that mean about this point and this point here? These are inflection points, right? Inflection points. What's going on DE?
Concave up.
You okay with that?
Yeah.
For any of these intervals we looked at so far, is the first derivative, like, has the first derivative been of the same sign? No. So again, I'm just pointing out that those two things are, yes, they're related to each other, but there are some ways in which you cannot make assumptions from one based on the other. So this is concave up. How about this E to P?
That's also funny.
Oh, I got.
That's concave up.
Uh-oh.
It's decreasing. F is decreasing, but it's concave up.
Oh, yeah, that's concave up.
Do we see that? let's look at the tangents. Let me actually draw them this time. So starting from the left, I probably shouldn't do that because I don't even think it's differentiable at that point. So let's get a little bit of clearance from it. Let's actually do it right though.
It's real.
Shouldn't be. Okay, so as I go from left to right, let's just do two tangents since I'm messing that up. What's happened to the slopes? They're getting bigger, right? So that is concave up again. Can I say it's concave up everywhere from D to P?
D to P, yes.
No. Why not?
Oh,
It's not that. See,
So what doesn't exist here? Which derivative?
The first.
Would be the second case. All right, so, and here's the annoying thing. Mathematicians can't decide if there's an inflection point in between those. Actually, never mind, there wouldn't be. Why not?
they're the same.
Yeah, they're both it's up on both sides. And then finally from P to Q, what's going on? Concave down. And the last thing I want to point out is, what can I say about F prime from E to P? F prime is negative the whole way, right? How about F prime from P to Q? Still negative, right? So it's decreasing the entire way, but the concavity is different throughout the interval. So again, yeah, just warning you to not to make assumptions from one derivative to the next. Any questions on any of the things we just threw out there, Jezreel?
Question, it's not about that, but at point D, is that a break in the graph?
No, it's continuous, but I would say it's not differentiable there.
All right. I couldn't tell if that was a break. Or
Yeah, it's kind of obscured by that vertical black line. Garrett?
Because it's not differential, is it
That's the thing that there's not consensus about. Some would say that, some would call it an inflection point, some would say that it's not. So I don't care.
what's it gonna be an exam?
We'll see. There's no good reason for me to throw those ambiguities at you. So for most functions, like the one I think we're gonna look at now, not yet. I don't know what my slides look like. Is this the same slide as last time? Cool. Blowing past that. All right. So polynomials. If I'm looking at a polynomial, am I ever going to have to worry about the thing that we just talked about, where you have concave up on this side, concave down on this side, but derivative doesn't exist between them? No. Polynomials, it will never behave that way. I can take as many, if I have a polynomial, I can take derivatives in infinite amounts, and they'll always be defined. So I want to find intervals of concavity for this thing. So by that implies that I need to do what? How do I get there? That's four. I need first derivative, right? So what is the first derivative of this thing? All right. Now what?
No, do it again.
Do it again.
Try to take a derivative.
Yeah, let's find a derivative of the first derivative, which is
36x squared minus 96.
96x minus 252. Right, and you set it equal to 0 because you're looking for what?
That's what it is.
You're looking for possible inflection points. Really, we're looking for. I'll leave it at that. So yeah, inflection points might be at what we find here.
It's not a guarantee.
Not a guarantee. Why would it not be a guarantee?
It's just not, if it's not differential, quote unquote.
Well, I mean, this.
It could also be, it could be concave up or concave down back to back.
Right. So you could have the derivative or the second derivative equals 0 and then be the same concavity on the other side. So the solutions to this equation might give me inflection points, but here's what's really true. If there are inflection points, this is how to find it. All right, so I got to solve this thing. Can I do any kind of, are there any common factors here between everything?
I assume 36 is not
Does 12 go into 252?
12.
Okay, so then I got 3x squared minus 8x minus 21 equals 0. That's the best I'm gonna do, isn't it? Yep. Cool. How does this factor? What numbers add together to give me, or yeah, what multiplies together to give me negative 63 and adds together to give me negative 8? Or does this not factor at all? It doesn't factor. Okay, so we'll just do it use the quadratic formula. So x equals 8 plus or minus the square root of 64 minus 4 times 3 times 21, or plus 4 times 3 times 21, which is 252 all over 6. And let's just approximate it. All right, so I'm pretty sure those are the two possible inflection points. But what do we need to do to make sure?
Second derivative.
Right. Well, input what? So if I put those back in the second derivative, I'll get 0. So what else can I look at? Maybe what I'm drawing here is a hint. So I know that when I take the second derivative at these 2 points, I'll get 0, right? So what else should I look at? Really, I'm looking for intervals of concavity, right?
Mm-hmm.
So how many intervals do I need to check? Or how many intervals do I need to check? 3. What are the intervals?
-50, 1.69 to 4, that, and then that's it.
Right. So basically, less than both, greater than both, and between. So I need to check these intervals. Do I need to check lots of points on the intervals, or what can I do? I just need one, right? So I found where the inflection points might be. So again, it would be impossible for the derivative for the second derivative to equal 0 anywhere inside. Otherwise, this would have found it. All right, so what's a good point to the far left?
1.
If you can help it, always use 0. How about between them? 2 or 3, and to the right. 5 sounds fun. Okay. So for the first interval, what is f double prime of 0? Negative 21, which hopefully that points out why I said always choose 0 if you can help it. So that is concave what? Down. All right, what is f double prime of 2?
Negative 25.
Something's going wrong here. I would expect them to alternate.
Yeah.
Oh, I know what I did. This is all my fault. So knowing that, I'm going to replace that 2 with a 0. And I'll replace this with a negative 2. So what did f prime of 0 told us that? Yeah. So f double prime of 0 was negative 21.
Yeah.
Okay. So now what's f double prime of negative 2?
7.
7? So what does that mean about that interval? Concave up. And you know what? I'm going to say this is concave up too. If you'll permit me this shortcut, this is a quadratic, right? Is this an opening up quadratic or opening down?
No.
Opening up, right? So it better go from positive to negative positive.
Yeah, and you can even check it by, if you know it's the very first polynomials to the fourth, so it's going to be doing
Yeah.
one of those.
Well, be careful, because if you were to graph the first polynomial, you can clearly see it goes from decrease on the so.
Yeah, but it's concave up, down, up.
Right.
If you have a positive leading coefficient, it'll always be up, down, up.
The concavity will?
Yeah. If it's to the fourth.
Okay. I agree with that. I misunderstood what you were saying at first.
No, yeah, sorry, that's one.
Oh, you're good.
Then you can check it.
If you're good with that, go with it. If you're not, then don't worry about it. I mean, that's kind of a big leap, I think, for most of us, for all of us to make right now. The thing I really want to focus on is, if you're looking at concavity, you're looking at what? What is the only thing that can tell you concavity about a function? Second derivative. So I mean, that's what we have to get our hands on. Here's something else the second derivative can tell you. Let's say we have a point C where the first derivative is 0 and the second derivative is positive. So let's try to draw what that looks like. So if the first derivative is positive, what can we say about the graph or the function? F prime is 0?
If it's 0, please. Oh. F prime 0 is not there.
Yeah, so what does that mean about the function at that? So let's do this. Here's the points. Here's the x value C. Let's try to think about what this function is doing, like around that point. If f prime is 0, what does that mean? It's switching from going. What switching from going up to down? The slope switching from going up to down.
Or the opposite, or
It doesn't have to, though. Yeah.
I actually based on this alone, then it could be a negative, or sorry, it could be a local min, a local max, or one of those saddle points, right? This one right here, I think, makes a couple of those impossible.
Same.
So the slope is 0, right?
Mhm.
But if the second derivative is positive,
Mhm.
what are the slopes doing around that point? They're increasing, right? So I have a horizontal tangent at this point, right? But what's happened to those tangents as I go to the right? They're becoming positive, right? And let's look at the other side. As I'm coming into this point from the left, what has to be true about the slopes? Well, they're increasing up to 0, right? Which means they must be negative preceding that point and positive after. So what kind of a point are we looking at? That's a local min. So here's another way to find your minima and maxima. If you have a critical point and the second derivative at that point is positive, then you know your function's going from, it has to be going from decreasing to increasing, which is what a local minimum is. I'll stop right there because that's kind of there are a couple of big leaps in there. Any questions on how I'm justifying that? What if I have a critical point, but the second derivative is negative at that point? That's a local maximum, right? So using the same type of logic, the slope at point C is 0, but the slopes are decreasing as I move from left to right. So they must have gone from positive to 0 to negative, which is going to form a local maximum. If they're both 0, or if f prime is C and f double prime doesn't exist, this didn't help you. You'll have to make your conclusion some other way. But this is another way that, if you're trying to find local minima and local maxima, the second derivative can help you get there. It's by no means necessary, but something you can use if you'd like to. Any questions on these conclusions here? Yeah. It's hard to say because you can't make any conclusions about saddle points based on this. Because if f double prime is 0, there are conceivable ways that you can have a minimum, maximum, or saddle point if both of those derivatives are 0. So if you run into that situation, you really didn't learn anything. All right, so I'm giving you this function here. I want to find lots of stuff: critical points, increase, decrease intervals, extrema, intervals of concavity. So I will let you all tell me how to start. What should I do first?
Basically start everything in calculus by getting a derivative.
What?
You basically start everything in calculus by getting a derivative.
I mean, almost everything. And so far? So I need a derivative. What is the derivative of this thing?
Product relationship.
Okay. So I'll just stop this for now. I'll let you tell me how to set that up.
F of x equals, g of x equals x to the power of the third. H of x can be 6 minus x to the 1/3, and then like sub functions there could just be 6 minus x and x to the 1/3.
Okay. I'm gonna try to, if you'll permit me, I'm gonna try to deal with h without breaking down. If let's see how it goes. What's the derivative of g?
2/3 x to the negative 1/3.
2/3 x to negative 1/3. What's the derivative of h?
6 minus x, negative 2/3.
Okay, so there's the outer, there's a derivative of the outer function, right? So yeah, I have something raised to the 1/3. The derivative of something raised to the 1/3 is 1/3 times something.
And then that's times -1.
Right, and now I have to take the derivative of the something, right? So all this times -1. All right, so based on my G and H and my G and H prime, I think I can do this. F prime of x is equal to negative x to the 2/3 So still kind of messy, but that's okay. All right, what would you like to do from here? To me, it doesn't feel clear where the critical points are yet. So here's something I might suggest if you're not already thinking it, is I want to try to make all my exponents positive.
Move to the bottom.
Yeah. So for this first term, that's going to be x to the 2/3 over 3 times 6 minus x to the 2/3 plus 2 times 6 minus x to the 1/3 over x to the 1/3. I dropped a 3. Yeah. Okay. That look all right? So looks a little less nasty, but still pretty gross. Anything else you would suggest?
Common denominators.
Common denominator sounds good. What would the common denominator be? I'm going to say it contains a 3, right? Do the other two factors there, the 6 minus x to the 2/3 and the x to the 1/3, have anything in common? Not really. So I just got to multiply those together. So 3x to the 1/3 times 6 minus x to the 2/3. And then what's the numerator going to look like? Oh, that was a happy accident. That becomes x, right? And this becomes 2 times 6 minus x. So that really worked out for us. How do you feel now about finding the critical points? How many critical points do you think we have?
So at least one.
Why is x equals 0 a critical point?
Then make it fine.
Okay, so critical points. X equals 0. Oh, the x equals 0. The derivative doesn't exist, but x equals 0. What's another one? I see at least one more x value for which the derivative won't exist.
Is it 6?
6. So, yeah, in the denominator, if x is equal to 0, the whole denominator becomes 0, but it also has x equals 6. All right, so I think those are the two places where the derivative will fail to be. How about, is there a place where the derivative will equal 0?
Yeah.
How can I find that?
Simplify the numerator.
Right, so This will only equal 0 when the derivative, or when the numerator equals 0. So x plus 2 times 6 minus x equals 0. X plus 12 minus 2x equals 0. Which I think tells me that x equals 12.
Mhm.
So a long way to go for critical points, right? But we got it. Let's just move down the list. How can I find intervals of increase and decrease? At double prime? You want to try that? Okay.
Wait, you said intervals of decreasing or increasing, that's it?
Yeah.
Do you not need that double prime for that?
I don't know if you need it. Could you use it?
You could, yeah.
You could, yeah. All right. How do you find second derivative? I think I'm actually going to throw the intervals concavity off this one, just for time and yeah, mostly for time. So let's do intervals of increase in the extrema. Which I grant you could use the second derivative to find the extrema. I don't know if that's the right tool for this job. That derivative is going to get out of hand. All right, so if I want intervals of increase and decrease, what should I do?
Plug in 4 values around, like in between each interval.
Okay, so let's make the intervals. Basically, I like to use this number line to basically split up all the real numbers. So what are my boundary points?
Negative infinity, 0, 6, 12.
Okay, 0, 6, 12. That's it, right?
Yeah.
All right, so I know at these two places the derivative fails to exist. But that does not mean the derivative changes direction from being, it might and it might not, so we still have to look. Derivative is 0 here. So what test point should we use?
-1, 1, 7, and
14. And I say use -1 and 1 if you can help it.
Yeah.
So now that I have those, what should I do with them?
plug them into the original function.
Right, so now we're looking for, what is f prime of -1? F prime of 1. And one thing kind of a practical concern that I'll point out. Do I care what these exact derivatives are? What's the only thing I actually care about?
Whether or not they're positive or negative.
Whether or not they're positive or negative, right? So, is the cube root of -1 positive or negative?
Negative.
Negative. Is 7 to the 2/3 power positive or negative? Positive. So you're dividing by something negative, right? Now you just got to figure out what the numerator is. Which maybe I should simplify that. Do I have enough time to rewrite this derivative over here so we can use it? F prime of x is equal to negative x plus 12, 12 minus x. That should tell you enough. So that's going to be positive divided by negative, right? So that should tell us that our derivative is going to be negative. So f prime of -1 is 0. So that is a decrease. So decreasing on what interval then?
Negative infinity to 0.
All right, f prime of 1. I heard someone say the start of the word positive, then they lost faith.
Yeah, it should be positive.
I think you should have faith. Yeah, so 12 minus 1 is positive. The denominator is going to be positive. So that's increasing on one interval. What's the interval that was associated with?
0 to 6.
0 to 6. All right, f prime of 7 is going to be positive divided by you say positive? So the numerator is going to be positive, right?
Right.
The cube root of 7 is going to be positive.
Oh, yeah.
What is negative 1 to the 2/3 power?
Negative.
Positive.
Oh.
That's so. Let me use a little more margin real estate to show you why. Negative 1 to the 2/3 power. Would you agree that's equal to the cube root of negative 1 and then squared? What's the cube root of negative 1?
1.
Negative 1. And squared is
1.
1. So
Oh, okay.
let me ask this, is it possible for 6 minus x to the power of 2/3 to ever be anything but positive? No, you're essentially squaring, right? You're taking the cube root as well, but you're squaring it. It's going to be positive. So that's kind of a shortcut we can use. So do we agree with f prime of 7 being positive? Okay. So it's also increasing on 6 to 12. So can I just say it's increasing from 0 to 12? Good catch. You cannot say that. Why can I not say it's like what's the problem? Why can't I say it's increasing everywhere from 0 to 12?
It does not exist at 6.
Yeah, you can't say anything about 6 itself. So I have to leave 6 out of that interval. And finally, f prime of 14. What's that one going to be? Be careful. Is the denominator positive?
Oh, no, yeah. It would be negative.
The denominator is positive, but you have 12 minus 14. So we are decreasing on what?
12 to infinity.
12 to infinity. Any questions there?
Bracket from 12 to 12 exists.
Good question. Why don't I put a close bracket on 12 if the derivative exists at 12? Because the derivative is 0 at 12. So it is neither increasing nor decreasing. It's a good question. All right, so I have all my intervals of increase and decrease. With the little time we have left, can I say anything about extrema? At least local extrema. Can I say anything? There's no local extrema?
There would be 1 at 12.
Why would there be 1 at 12?
Because that's a 0.
What do you mean by it's a 0?
I mean, it's derivative equals 0.
Is that enough?
Because it goes from increasing to 0 to increasing.
That's the whole picture. It's not enough to say the derivative is 0, therefore there is a local extreme. The derivative has to be 0 and it has to be increasing one side, decreasing the other, which you have at
12. At 12.
you have at 12. Do I have it anywhere else?
No, 0 exists.
Yeah, you do have it.
So I would still call this a minimum. It's just not differential at the minimum.
Which is still one of the things you could use for.
Yeah. So remember,
It's either D and E or 0.
right. So remember where local mins and maxes exist. They exist at places where the derivative is 0, which is like the most common thing, or where else?
Or the derivative does not exist.
Where the derivative fails to exist. And one more thing I'll say to amend that, they might exist there. For example, the derivative fails to exist at 6, but it's increasing on both sides, so that can't be.
Mhm.
That can't be an extreme. All right, so I better stop there. I believe that you could plug into the original function and find those coordinates. All right, so that is the end of 4.3. We'll start 4.4 next time. Go do the mastery test thing if you haven't already looked at it.
Oh, the mastery test, that's just on campus. You just take it.
No, the practice
Okay.
thing is on campus. The test is here.
The test on